All right, so for my topic, I'm covering the extreme value theorem. So the extreme value theorem states that if f is continuous on a closed interval a to b, then f attains an absolute minimum at values f of c, an absolute maximum of f of d, where c and d are some values in the interval of a to b. So what does that mean? That pretty much is saying that if the function's continuous and it's on a closed interval, meaning that both endpoints are included, then there is an absolute maximum and an absolute minimum in that interval. So for instance, you can see that in the first graph right here. Let's say we're taking it from the closed interval a to b. We can, using the extreme value theorem, we know for a fact that there will be at least one absolute maximum and at least one absolute minimum. So you can tell by this graph right here from this interval with the dotted lines, you can just point out the minimums right here and then the absolute maximums right there. Similarly, if we were to take the closed interval from a to b on this function, we know it's a continuous function as well. And since it's a closed interval with the endpoints included, we can conclude that a is the absolute maximum, or f of a is the absolute maximum, and f of b is the absolute minimum. There are a few points to note regarding the extreme value theorem. One, it does not work on intervals that aren't closed. So for instance, if you have a function where x approaches infinity on both sides, then you cannot apply the extreme value theorem because we really don't have a specific maximum on this case because the function will just continue to go up, and same on this side. And then likewise, if this interval is clearly not closed, and the absolute minimum would have been here and the maximum would have been here, but clearly you can't attain a specific value because the endpoints are closed. And then another point to note is that it does work on horizontal line functions. So you know that, let's say this is an endpoint, this is the endpoint, and it's a closed interval and it's clearly continuous. You can still apply the extreme value theorem here, except that all the points on this function would qualify as an extreme absolute maximum and minimum. Next is also the function doesn't work if, or you can't apply the extreme value theorem if the function is discontinuous. So for instance, if you have a hole like this one, this is where the absolute minimum could have been. And as a result, you cannot confirm with the extreme value theorem. And then likewise, right here, if the function is discontinuous, as you can see right here by this vertical asymptote, you can apply the extreme value theorem. And one important point to note is that the extreme value theorem only confirms that there is definitely a maximum or minimum on this closed interval. That doesn't mean to say that if you can't apply the extreme value theorem, then you automatically do not have any absolute extreme on that interval. In fact, you can have some. For instance, if this discontinuity was, say, up here, you can still have that absolute minimum. However, if you can confirm that the interval is closed and you have a continuous function at hand, you can guarantee there will be a absolute minimum or maximum, and maximum on the interval. So let's start with a few examples. So the first one being, can the extreme value theorem be applied on the function y equals 3x squared minus 5 on the interval, closed interval from 0 to 3? So step one is to check to see if the function is continuous. And we can confirm that it is yes, because we're dealing with a function that is a polynomial. And we know that all polynomial functions are continuous for all x values. So that is a yes. And then the second step we want to do is check to see if it's a closed interval we were dealing with. And as you can see, it's a closed interval from 0 to 3. So that is yes as well. So the answer is yes. The extreme value theorem can be applied here. And then as a result, we can guarantee that there will be a maximum and a minimum, an absolute maximum and minimum on this interval. Another example has to deal with the closed interval method. So pretty much the problem is check to see if you can apply the extreme value theorem for f of x is equal to 2x to the fourth minus 4x cubed on the interval -2 to 2 If yes, find the absolute extrema. So here we start to deal with the closed interval method as well, alongside the extreme value theorem. So first step is to see if the extreme value theorem applies. So first step is check to see if the function is continuous. Once again, we're dealing with a polynomial, so we know that the function is continuous. And then check to see if the interval is closed, and as you can see, it's -2 to 2 on a closed interval, so we can confirm that there will be absolute extrema on this interval. So the next step is to use the closed interval method, which is something that's very closely related to the extreme value theorem. This involves finding the values of, finding the critical points, and then also finding the values of the function when for the endpoints. So here, we start off by finding the critical points. So first we start off by finding the derivative of f of x. By using the power rule, we can get that it is 8x cubed minus 12x squared. And then to find the critical points, given that we know that the function, the derivative function exists for all points, the next step to find the critical point is to see where the derivative equals 0. So you set it equal to 0, and then you get that the derivative is equal to 0 at 0, and then 3/2. So now what we want to do is find the associated y values of the original function with the critical points and then the endpoints. So we find f of 2 to be 64, f of 0 to be 0, f of 3/2 to be -3.375, and f of 2 to be 0 as well. So here what we did was we plugged in the critical points right here and here, and then we plugged in the endpoints here and here for the original function, which was 2x to the 4th minus 4x cubed. After doing that, we clearly see that f of -2 is the highest value, so therefore we can conclude that it is the absolute maximum on this interval. And then f of 3/2, or f of 1.5, has the lowest value of a -3.375. So we can conclude that is the absolute minimum in this case, because they're the two lowest values. And yep. So based on the extreme value theorem, we were able to conclude in this problem that there is definitely an absolute maximum and minimum. And then using another method that's tied in with the extreme value theorem, we were able to actually find the exact absolute extrema. So now we have to answer the question, how does it tie with the material that we've learned previously and have learned after this? So as we just did, it's very closely related to the closed interval method, because in order to find the actual absolute extrema, you use that method, because what extreme value theorem does is it lets you confirm that there is absolute extrema, but the closed interval method lets you actually find those values. And then the next thing that is related to is critical points, obviously, given that we have to use that for the closed interval method, and then it ties in with derivatives as we've done this whole semester, and it also ties in with the idea of continuous functions and everything, because you need to confirm that it is a continuous function in order to apply the extreme value theorem. And that's it.